Welcome back. So, we will continue the discussion on wave equation. In the context of semi group. So, last time we studied some classical theory, namely this conservation of energy for the wave equation, and that is our starting point. So, with that basis, now we go on to construct the semi group associated with wave equation, conservation of energy. So, let me just recall that. So, this is u t t minus Laplacian u equal to 0 in R n t positive, and the initial conditions. So, u x 0 equal to f 1, u t x 0 equal to f. So, when f 1 f 2 are smooth, using Fourier transform we can write down the solution of the wave equation. So, if omega is in R n, so we define this thing. So, energy of u in omega at t. So, this is that u t square, let me just write it once again, plus grad, this is only with respect to x, u x t square dx. So, u is the solution of the wave equation. Maybe one has to put half for the correct things, but okay, that is. So, what we saw was, for if f 1 the initial conditions are smooth functions with compact support, then the energy is conserved. R n at t is equal to at t equal to 0 for all t. In fact, since the wave equation is invariant under the mapping t going to minus infinity, okay. So we can take for all t bigger than r. Okay. So, the energy is conserved. So, this is our starting point, and now here we have taken f 1 and f 2 smooth. So, you want to just complete, we want to take completion of that space with respect to this energy norm, okay, in this that sense. So, last time I defined that. Okay. So, let H d be the completion of so everything I am doing in the free space. So, completion of this C c in the norm. Okay. So, that is Dirichlet norm. So, let me put that as let me write d. Okay. So, this is just integral, let me write it once. So, everything is in integration is also over R n. Okay. So, this is just So, I made a few remarks about this. This is also a Hilbert space. So, HT is a Hilbert space, and it is larger than H1 Rn. Okay, so, that is one thing, and this I made a comment. So, HD is not a subspace of D prime R2, but HD is L2 loc Rn for n bigger than or equal to 3. Okay. So, we are working only in n bigger than or equal to 2. So, this forces us to choose the domain of the generator carefully. And as far as the second component, so this is the first component, namely F1. Just if you look at the energy, so this at t equal to 0, this will give you F2, okay, and this gives you F1. This comes from F1. So, F1, the the first initial condition, that is the position, and this is the velocity. So, that is in HD, and the next one is in L2. So, that is fine. So, we consider so let me just so let H is HD cross L2. Okay, so this C infinity C cross C infinity, C is dense in H. Okay, so this, so H is also a Hilbert space. So, let me just write an element in this Hilbert space. We denote by, so there are two components. So, this I will write in matrix notation. So, it will be clear why we are writing that, an element in H. So, this first component is in this HD, and the second component is in L2. Okay. So, what we have seen and okay, let me write the inner product and norm once at least. So, that inner product. So, if you take Fg in H, okay, the first component. So, this is F1 F2 and this is G1 G2. So, the first component are in HD. So, this let me write that, okay, Fg. So, since there are many spaces, so let me just write that H. This is nothing but integral grad F1 dot grad G1. So, we can also put a complex conjugate. Okay, I am not putting that, but strictly speaking we should put that if we are considering complex valued functions. And the second component is simply that F2 G2. Okay, because both are in L2. Okay, so, the norm, so F H square. So, let me write that. So, this is grad F1 square plus F2 square. So, this is the inner product and that is the norm. So, what the conservation of energy tells us that this mapping, okay, the conservation of energy So, let us rephrase that. So, you take this mapping F1 F2 and map it to the solution of the wave equation with these components. Okay. So, at least when this f is in F1 F2 in C infinity, that implies norm of u u t in H is equal to norm of F1 F2 . So, the solution of the wave equation, though the initial conditions have compact support, in general the solution in y in general it is does not have compact support. As t grows, in fact, the support of u grows, but nevertheless the energy integral remains finite, and this is what the conservation of energy tells us. Okay. And now we want to extend this relation to H itself. So, now we want to take this f in this H and again map this to the solution of the wave equation, and we want to get this conservation of energy. Okay. So, that certainly we can do, because this C since this C infinity with compact support is dense in H, we can certainly so this I call this mapping as U. Okay. So, let me just call that. We can extend U by density and continuity. Okay. So, this U now f again F1 F2, but this is in now H, and I want to map this to U u t, again that is in H. So, this is the question. Certainly we can do that, but that's so this in fact it depends on t. So, this for every t we can do this. So, this I will write as t. The only question is, why should this mapping be only of this form? Okay. We should be able to take a pair in H and map it to another pair in H. Okay. So, we will come to this question little later, but with this understanding let us calculate the generator. Okay. So, I have not yet proved that that is a semi group or group, but let us heuristically compute the generator. So, what is generator? If you recall, so we can write that as d by dt of u t f at t equal to 0. Okay. So, this is another way of writing that, but by definition this d by dt is nothing, this u t f is nothing but u u t. Okay. Just for the time being, except that that is the mapping, and this since u is a solution of the wave equation. So, this is nothing but u t t at t equal to 0, and this u t at t equal to 0 certainly we can easily get that, that is f 2, and this one, since u satisfy the wave equation. So, this is Laplacian u, and again at t equal to 0. So, that is heuristically that is what we should get. Okay. So, the generator, so this I can, so this I write this as this matrix for Laplacian 0. Okay. So, that generator, so I call it G, is of that form. Okay. Of course, this thing you can get directly from the equation itself. So, if we just write this equation as a system, okay, so this implies first order system. So, this u t, same thing we get. Okay. So, this is u t, this is u t t, and that is Laplacian u. So, just you get. So, this is Laplacian. So, again you get that. U t. So, in fact, if we write this system form, we do get this in the form of abstract Cauchy problem. Where now the operator is given by this G. Okay. And now yes, the same. So, here also the heuristically we got directly from the wave equation through that conservation of energy, but here just by writing a system we get that. Okay. So, with this motivation, now our task is so our task is to show that G generates a unitary group okay, and then connect this group to, then connect this analysis to the wave equation. Okay, that is our final thing, right. So, we have to somehow connect this to wave equation, solution of the wave equation. Okay. So, in order to show that, so we have to carefully choose this generator of this G. Okay. So, the domain of G. So, let me just okay. So, dg, of course, dg is a subspace of the Hilbert space H. Okay. So, again the elements will have two components. So, this is, let me write that. So, F, this is F1, F2, two components, they are all in H, okay, such that. So, look at here. Okay. So, what is the definition of the, okay. So, if G is this one, so this G of F is just nothing but F2 okay. So, where F is F1, F2. So, the second component becomes the first component under that mapping G, and if that has to belong to the Hilbert space H, this F 2 has to be in the space H D. Okay, so let me write that first, that is easier part. Okay, so this is H D, and the second part is Laplacian F 1, so that should be in L 2. Okay, so this is again in this in the Weak-Shuns. In the Weak-Shuns, as I commented last time, so we do not fully understand the nature of elements in HD, only through that completion process we understand. Okay, so since HD is not even a subset of D prime Rn, at least in case of N 2. So, what we should do is this is in HD. So, let me write that HD intersection D prime Rn. So, this is the first component, and then cross L 2. Okay. Fine. So, this is only necessary and only necessary if n is equal to 2. If n is bigger than or equal to 3, we know that the elements of HD are L2 log functions. So, automatically they have weak derivatives, and we want this weak Laplacian to be in L2. Okay. So, here is the theorem. Okay. So, that's theorem. G with domain of definition, dg is skew symmetric, skew adjoint. Okay, skew adjoint. So, that is G star is minus G by Stone's theorem. So, this we have already studied, Stone's theorem. G generates a unitary group. So, the task is only to show that this operator G, so G is, so again you keep on writing that. So, dg into H. Okay. So, let me again recall some operator theory we did some time back. Okay. So, when do you conclude that an operator is self adjoint or skew adjoint? Okay. So, let me again recall. Okay. So, maybe okay, let me V is not V. Okay, let me just, so A from dA, this is a subspace of H into H, okay, linear operator, closed densely defined symmetric operator. Okay, so that means just AXY is XAY for all XY in domain of A. Okay. So, we say that this A is self adjoint under these conditions. So, if A is a closed densely defined symmetric operator in a Hilbert space H, then A is self adjoint if and only if this plus or minus I belongs to rho. In fact, there is a simplification with this all the properties of this thing. So, even to show this thing need to show suffices to show image of this I plus or minus I minus A is dense in H. Okay, you just recall. So, this we already done that. Okay. So, what is the connection between self adjoint and skew adjoint? It is very simple. Okay. So, put B equal to, so plus or minus I A. So, then A is self adjoint if and only if B is skew adjoint. Okay. So, just this multiplication by plus or minus changes self adjoint to skew adjoint. Okay. So, we can now just transform this condition on A to B directly. Okay. So, that is what we do. Okay. So, suppose B is a densely defined closed skew symmetric operator in a Hilbert space. So, skew symmetric means, again let me just write that B x y is minus B x b y for all x y in domain of P. Okay. So, then B is skew adjoint if and only if this plus or minus 1 belongs to the resolved set. Okay. Again this you can write in terms of the image. Okay. So, this in order to show that under this condition that B is densely defined closed and skew symmetric. So, again suffices to show this image of, so plus or minus I minus B is dense in the Hilbert space, whatever Hilbert space we are studying. Okay. So, with that recalling, now we proceed to prove this, let me just comment on the proof and then we will. So, about this G. Okay. So, just okay. So, proof I will just begin, we will continue in the next class. So, we show G is, so the first one G is skew symmetric and this image of plus or minus I minus G is dense in H. Okay. So, this H of course is the one we started with. Okay. So, this is easy to verify that G is densely defined closed operator. Densely defined, already we have seen that densely defined closed operator. Okay, because this C infinity C cross C infinity C is in DG and that is dense in H. Okay. So, we will continue with this. Thank you.